Hello everyone, my name is Yiyang Chen, a PhD student from Tsinghua University and the first author of this paper. Today I'm going to present our work, IDFuzz Intelligent Directive Gray Box Fuzzing. This paper is about directive fuzzing, an important branch of fuzzing. Directive fuzzing aims to test specific target code size in programs. Typical application scenarios of directive fuzzing include crash reproduction, candidate vulnerability confirmation, and patch testing. One big goal of directive fuzzing is to reach the target code as quickly as possible. So, many existing directive fuzzers use a fitness metric like distance to prioritize Cs, but they usually pay little attention to the directness of input mutation step. They often adopt a strategy that randomly choose offsets and length during mutation, which prove to be inefficient in directive fuzzing context. Our work proposed a novel input mutation strategy that intelligently identifies critical input fields to mutate. Our key insight is we can identify critical fields for mutation based on past mutations. For example, we have fuzzing input A with distance D. When we mutated at byte position X with a changing value operation, it generates input B with a smaller distance, D minus 1. So, we can learn some useful knowledge here, which is the critical field of input A is located at offset X with length 1. With this knowledge, next time, when we mutate the input A, we may probably mutate the critical field directly rather than making blind attempts. However, based on this insight, we still have two key questions to answer in order to develop a practical mutation strategy. First, is this knowledge applicable to future mutations? It seems that this knowledge can be highly specific to certain inputs, like input A in the example, and it lacks generalizability. Second, can this knowledge help the fuzzer to reach unexplored code regions? This is because the knowledge we gain only helps us reach distances that have already been reached. It may not guide the fuzzer to reach unexplored code. In our work, we give affirmative answers to both questions. For question 1, we achieve generalizability by using a neural network model to learn the high-level pattern between how the input bytes are organized and their distance. For question 2, we use a novel presentation of program branching behaviors and let the model learn to reach an unexplored code from covered sibling branches. We use an example to show our basic idea. This real-world example is part of JHAT program for reading a JPEG format input file. The vulnerability located at line 24, and we need to mutate the marker byte to mcom in order to reach the target. And the marker byte is the first non-padding byte with length 1. As we can see in this example, due to the nested loops and the padding bytes here, neither symbolic execution nor taint analysis is effective in this example. So, what we do is we've used a neural network model to identify the marker byte. First, we compute the input distance as an output. For inputs that do not re-switch, we give them distance 1. For inputs that re-switch and take the case mcom, which are the exactly inputs we want, we give them distance 0. And notice that for inputs that re-switch but take other cases, whose distance is supposed to also be 1 in existing directive fuzzers, we give them different values between 0 and 1 to distinguish their branching behaviors. Then we model the relationship between input bytes and distance using a neural network model. We set the values of input biases in input and the input distance as in output. Since we assign different values to different other cases, even if we don't have a zero distance input, we can probably find the marker byte, which causes the different values between 0 and 1 when taking other cases. Finally, we compute the model gradients to identify the marker byte. This is based on the mathematical explanation that changing the marker byte has the greatest impact on input distance. So the marker byte is theoretically associated with the largest absolute model gradient value. Thus, we can identify the marker byte by finding the largest absolute model gradient value. The key idea of IDFuzz is, first, we model the relationship between input bias and input distance using a neural network model. Then, we identify the critical bias or field by locating the maximum model gradients. This gradient-guided mutation strategy is inspired by news. However, we solve the unique challenges in the specific domain of directed fuzzing by introducing several new techniques, including branch encoding for model initialization, adaptive dataset generation for model training, and gradient filtering for gradient-guided directed mutation. In model initialization, we first extract the coverage of dominating basic block to reduce the dimensionality and develop a branch encoding technique to accurately represent their branching behaviors. This branching encoding technique uses a proper fraction between 0 and 1 to encode covered sibling branches, which enable us to learn to reach an unexplored branch. In model training, we develop an adaptive dataset generation technique to obtain a small yet sufficient dataset. We first prune early accumulated inputs that cover very few non-BBs, and then we reduce inputs by leveraging the similarity in byte distributions among relative seeds. In the gradient-guided directed mutation step, we develop a gradient filtering technique which help us to eliminate real-world noise caused by uneven input byte distributions, including large gradients for magic bytes in the file format and critical bytes for neighboring non-BBs. And then we use a DB-scan clustering algorithm to group critical bytes to critical fields for better mutation effectiveness. In our evaluation, we evaluate IDFuzz from aspects of efficiency, roles of each component, and its runtime overhead, as it involves neural network model training. For research question 1, we use Google Fuzzer Test Suite as our benchmark, and we choose AFL-Go, WinRanger, Bingkai, and SelectFuzz as baselines. Notice that we didn't build IDFuzz as an independent fuzzer. Instead, we implement IDFuzz as an input mutation module and equip the baselines with IDFuzz. And we can see that IDFuzz gives at least 2 times speedups to these baselines in reproducing targets in Google Fuzzer Test Suite. And for research question 2, we also found that the 3 new techniques, including branch encoding, adaptive dataset generation, and gradient filtering, they all have clear contributions to IDFuzz performance. And we only observe a 6% increase in runtime overhead, even if IDFuzz involves neural network model training. For the example we earlier mentioned, considering an average file length of nearly 500, we only need 6 attempts to successfully locate the marker byte to mutate, which can save huge amount of fruitless mutations. Using IDFuzz, we found 6 new vulnerabilities and 1 incomplete fix, including 4 CVs granted and 2 high severity vulnerabilities. To conclude, our contributions include a new finding that we can identify critical fields for mutation based on past mutations in directed fuzzing, and we build a prototype of IDFuzz with very solid empirical results. More details can be seen in our paper. Thank you.